Welcome to this video about triangle and circle. We will classify triangles based on the measures of their angles and based on the lengths of their sides. We will learn how to draw a circle that passes through the vertices of a random triangle. Finally, we will conclude the area of the triangle and the area of the circle, and we will finish with a practical exercise. If you like this video, please subscribe to the channel and push the bell button to receive notifications for the new videos I upload to the channel. So let's start. Classifications of triangles according to the measures of angles. So basically, we have three types of triangles based on the measure of their angles. The first type is the acute angle triangle. In this triangle, we have three acute angles, meaning that each of them has a measure or a size that is less than 90 degrees. The second case is the right-angled triangle. In this type of triangle, we have one angle with a size of 90 degrees, and the rest of angles are acute, meaning each of them has a measure that is less than 90 degrees. The last type is the obtuse angled triangle. In this triangle, we have one angle with a size that is larger than 90 degrees, and we call it an obtuse angle, and we have the two remaining angles. Each of them has a size that is less than 90 degrees. Now, after we finished the classification of triangles according to the measures of angles, let's move to the classification of triangles according to the lengths of their sides. So we have also three types here. So we start with the scaling. In this type of triangle, the length of all sides are different. The other type is the isosceles. In this triangle, the length of two sides are equal, but the length of the last or the third side is not equal to them. So only two sides are equal. In the last type, we have the equilateral triangle, in which the length of all sides are equal to each other. Here is very important to note that in every triangle, regardless of its type, the measures of angles always add up to 180 degrees. So let's take from the previous cases we discussed when classifying triangles according to the length of their sides, the isosceles and the equilateral triangles. The isosceles, if we see here, the picture on the right, we call this triangle ABC. The angle A, which we see here, which is formed from the intersection of the two sides with equal length, in our case, they are AB and AC that form the angle A when they interact here with each other. We call this angle the vertex angle in the triangle. And we call the remaining two angles, B and C, which we see here, the base angles. Another property in the isosceles triangle, if the isosceles triangle is also a right-angled triangle, meaning that the vertex angle is 90 degrees, then each of the base angles is 45 degrees. So if we have this triangle here, the isosceles, and let's call it A, B, C, where A is the angle with the size 90 degrees, here we have the length of AB is equal to the length of AC. In this case, each of C and B has a measure which is equal to 45 degrees. And this is, of course, obvious since we know that A plus B plus C equals 180 degrees. So if A is already 90 degrees, this means that A plus B, 90 plus B plus C equals 180 degrees. And from this, we conclude that B plus C will be equal to 90 degrees. And since in the isosceles, the angles of the base are equal to each other, then each of them will be equal to 45 degrees. Now let's take the value, let's take the case, of the equilateral triangle in which all the sides have equal length. In this equilateral triangle, all angles have equal measures. Each of them is 60 degrees. And we can notice that 60 multiplied by 3 will give us, again, 180 degrees. So let's take this test. This is an isosceles triangle on the right, in which the length of AB is equal to the length of AC. Knowing that the circumference is 19 centimeters and the length of BC is 5 centimeters, then calculate length of AB and length of AC. So here we have the length of AB plus the length of AC plus the length of BC is equal to 19 centimeters. We substitute the length of BC by 5. From this, we conclude that the length of AB plus the length of AC equals 14. Since the length of AB is equal to the length of AC, we can treat them as x value, which we want to solve this equation for. So we get 2x is equal to 14, and this gives us x is equal to 7, which is the length of AB, and at the same time, it's the length of AC. Now let's move to the other exercise. This is an isosceles triangle here on the right, in which A is equal to 50 degrees, which is the vertex angle in this triangle. Now we need to calculate B and C. So usually they use this small sign on top of them to refer to that B and C are angles. So here we have, as we have seen, A plus B plus C is equal to 180 degrees. I can treat B and C as x value, which I want to calculate, since they are the base angles in an isosceles triangle, meaning that they have an equal measure. So this will give me A plus 2x equals 180 degrees, since this is treated as x and this is treated as x, since they have both equal measure. Now I substitute A by 50, so I get 50 plus 2x is equal to 180 degrees. From this, I get 2x is equal to 180 then I move 50 to the other side, so I get minus 50, and 180 minus 50 equals 30. From this, I get x is equal to 15 degrees, which is the size of B, at the same time the size of C. We can make sure that our work is correct after finding out the value of or the missing value of the two angles by adding 15 plus 15 plus 50, which is the size of A that is given in the beginning. This must be equal to 180 degrees. You see here, then we have a mistake here. 30 plus 50 equals 80. It means that I have made a mistake here in this equation. I forgot to put 1 here. So 130 divided by 2. This will give me 65. Now 65 plus 65 plus 50. 180 degrees. So my work is correct. Now draw a circle that passes through the vertices of a triangle. Regardless of the type of this triangle, we need to draw a circle that passes through its vertices. Before we talk how we can do that, let's remind ourselves with the concept of the perpendicular bisector. So if we can see here that the perpendicular bisector of a side of a triangle is a line that is perpendicular to the side and passing through its midpoint. So let's forget about this for a while and see this shape here. So if I considered AB to be one side of the three sides of a random triangle, then if I measured the length of this side AB and divided it by 2, then I choose a point, let it be M, that falls on the middle of AB, and from this point I draw a vertical line, or in other words, a line that is perpendicular to the side AB. Then each point from this line that we call here the perpendicular bisector of AB falls on the same distance from both sides. So in other words, we will have the length of M2B is equal to the length of M2A. Similarly, if I choose another point here or here, I will get the same thing. For example, here I chose the point M1, so I can get the length of M1A will be equal to the length of M1B. So now let's take this side and see, for example, this triangle. In this triangle, we notice that we have 3 acute angles. So if we take each side from the triangle, and we repeated the previous trick here we talked about, so that I measure the size, I measure the length, if we can say, of this side, then I choose a point here in the middle and I draw a vertical line. Then if I repeat the process for all sides, then we notice that those vertical lines, which I call the perpendicular bisector of the sides, meet in a certain point here. In this case, or in other words, in the case of the acute angled triangle, those perpendicular bisectors of the sides meet in the middle, inside the area of the triangle. And in this case, if this triangle is called ABC, then, and if I call this point M, then the length of MB is equal to the length of MC and is equal to the length of MA. Remember this for the next slide. So here I have another case. I have a right-angled triangle. In this case, if I repeat the process, then I find that the point M will fall here. And in the case of the obtuse angled triangle, the three perpendicular bisectors of the sides meet at some point that doesn't fall on the area of the triangle. So they meet outside of the area of the triangle. So as we have seen, this point in each case of the previous three cases, this point M here falls on the same distance from all vertices. So if I call this A and B and C here, so the length of MA is equal to the length of MB and is equal to the length of MC. Why? Since it falls on the perpendicular bisector of each side. So again here, if I call it like that, A, B, C, I will find that length of MC is equal to length of MB is equal to length of MA, and here the same, A, B, C, and I have M. The length of MA is equal to the length of MB is equal to the length of MC. So I can treat M as the center of the circle that passes through the vertices of each of those triangles, since I have here length MC is equal to the length of MA and is equal to the length of MB. So each of them, I can call it a radius of the circle that passes through the vertices of the triangle. And same applies to the other two cases. Now, let's learn how we can conclude the area of a triangle. So let's forget about this for a second and get here to the right. Let's draw a triangle like this one, a random triangle, and draw its altitude or its height here, which is the vertical lines that falls from or that is drawn from the vertex, from one of its vertices to the base. So let's draw this random triangle on a piece of paper. Then let's use a scissors to cut this triangle, and we make two copies of it. This is the first copy and this is the second copy. We leave the first copy as it is, and we cut the other copy into two triangles. This is the first one and this is the second one. So now we have this triangle here is moved to this red triangle as it is. We didn't do anything, we didn't do any cutting here. And then after we cut this triangle, we got two parts. This part, we put it here. This is X, and this part, we put it here and we denote it by a circle. So now we notice that we got a rectangle. It has this length and this width. The length of the triangle, of the rectangle, sorry, is the base of this triangle. So the area of the triangle, the rectangle, sorry, area of rectangle will be equal to the length of the base of the triangle multiplied by the height of the triangle. Let's call it h. You see, because this height of the triangle is equal to this to the width of the rectangle, so multiplied by h. So this is the area of the whole rectangle we got at the end of fitting the two copies of the same triangle. From this we conclude that the area of the triangle will be equal to half of this area of the rectangle, which will be half length of base multiplied by h, which is this we have written here. Now let's take a simple test. In the above triangle ABC, the area is 3 square meters and the length of base is 3 meters. Find h, which is the height or the altitude of the triangle. So based on this law that we concluded, the area of the triangle ABC is equal to half the length of base multiplied by h, and this is equal, or we can conclude from it, we have the area is 3 square meters. This is equal to half multiplied by the length of base, which we are given, and it's 3 multiplied by h. We can divide by h, by 3, we get here 0, so 1 is equal to h divided by 2. This gives us that h is equal to 2 meters. So this is the height of the triangle. Now we want to conclude the area of a circle. We divide the area of a circle into a very large number of smaller parts. And let this number, for example, be n. Then each part could be approximated to a triangle. So here, in this example, we have taken one piece of those small pieces that count to number n, and since this length is very small, we can approximate it to a straight line that forms the base of this small triangle. And then we can conclude that the area of this small triangle will be equal to half multiplied by the length of the base I multiplied by r. I can take values 1, 2, 3, 4 to n, which is the number of parts we have divided the area of the circle by. Now the area of the triangle I is equal to half multiplied by base I multiplied by r, exactly like this one. And the area of the circle will be equal the sum of the areas of all those small triangles. In other words, half multiplied by the length of base 1 multiplied by r, plus half multiplied by the base of the second triangle multiplied by r, and we continue with similar manner until we reach half the length of base n multiplied by r. Now, since half is a constant, we can remove it out. Also, r is fixed, so we can remove it out or remove it outside of the brackets, and inside the brackets we will be left with base 1 plus base 2 plus we continue until plus base n. And this sum here we see between the brackets is nothing but the circumference of the original circle, and we know that it equals 2πr. So we get now the value between the brackets. Instead of this sum, we have 2πr. This is multiplied by half multiplied by r, so we end with p multiplied by square r, or by p multiplied by r squared. And this is the area of the circle. So let's calculate the area of the colored part in both shapes we see here. So let's start with the first shape. The area of the blue part is equal to the area of this square we see here, and we know that it's a square since its length is equal to its width and is equal to 5 meters. So it's equal, the area of the blue part is equal to the area of the square minus this part, which is the half area, the half of the area of the circle. And this is equal to, so the area of the square, it's 5 multiplied by 5 minus half the area of the circle. The area of the circle, as we just learned, is p multiplied by r squared, and this is equal to 5 multiplied by 5 is equal to 25 minus half multiplied by p, which is approximately 3.14, and multiplied by r squared. So if this is 5, it means that this is 2.5. So it's 2.5 squared, and we do the calculation. And the result has the unit of squared meters because it's an area. Now let's move to the other shape where the area of the blue part is equal to the area of the parallelogram we see here. If you like, you can watch my videos, parallelogram part 1 and 2, in order to see how we concluded the area of a parallelogram. So it's the area of the parallelogram minus the area of the circle we see here. So the area of the parallelogram equals the length of the base of the parallelogram, which is 14, base of parallelogram, multiplied by the height of the parallelogram, which is 8. So we will have here area of parallelogram is equal to 14 multiplied by 8 minus the area of the circle, which is pr squared, p multiplied by r squared. So this is equal to 14 multiplied by 8 minus, we approximate, or can say we approximate this because p is approximated to 3.14 and multiplied by The radius here is half 8, which is 4. So multiplied by 4 to the power of 2. We do the calculation, and the result is the area of the blue part. I will put a link to the videos, Parallelograms Part 1 and Part 2 in the description box. Please feel free to watch these videos. Thank you so much for watching.